Welcome back. In this video we're going to be looking at another example problem, but with multiple LEDs in series. You might want to do this to increase the brightness of an indicator light or a flashlight, for example. This is similar to the previous example problem we had, but with multiple LEDs for our load instead of multiple resistors. This becomes more apparent when we use our approximation for our LEDs that we determined in video 1 of this series for our LEDs. And you'll see that we have 3 resistors in series like in the previous example video, but with the added 2 extra voltage sinks. Now, you might have noticed that we haven't chosen the voltage for our voltage source yet, and that's because this is one of the goals of this video. Sometimes it's up to you to decide how much voltage you need to turn on the circuit. And that's what we're going to be trying to determine. To start this off, let's start by looking at all the voltages summed together in the loop, using Kirchhoff's voltage law. You'll notice that the source voltage is positive and all of our load voltages are negative. Now, we can move all of our loads over to the other side, and we'll see that the source voltage has to equal all of our loads added together. We can also break up the voltages of the LEDs into their separate approximated components. Now, one of the things I wanted to do in this video is relate the calculations, the math, and the circuit all together, and show you how moving things around changes things in the circuit. You can see here that we can represent commuting the voltages as commuting the components in the circuit. Let's watch that one more time. You see that we have 2 voltages. We can add these together, and this is the same thing as combining both of the voltages in the schematic together into one voltage sink of 3.68 volts. By substituting in Ohm's law, we get our currents and resistances throughout the circuit. Since this is one big loop, we have the same current for each one of our component. And by factoring out that current, you'll notice that we can combine the resistances for our LEDs. Putting them together, we get a total resistance for both of our LEDs combined of 144 ohms. You can also see the combination of this in the schematic. We have one more thing we need to determine to get the voltage for both of our sets of components, the current. If we know that, then we can know all the voltages. By solving for current, dividing over the resistances, we get an equation for current. And notice we know every single term except for the voltage source. So the question is, what voltage source should we pick? If we plug in 3.68 volts, then we would get 0 amps, which means that nothing's going to turn on. So we need to pick something bigger than that. Let's say 4.5 volts. Now, this would equate to a current of 3.36 milliamps, which should be enough for both of the LEDs to turn on. Now, we can calculate the voltage across the resistor and the voltage across the resistance of the LEDs. Adding on the voltage from our voltage sink of the LEDs, we get a total voltage across both of the LEDs of a little over 4 volts. Now, let's check this out with measurement and see how close we are. Alright, so I have our setup here with 2 LEDs in series, a 100 ohm resistor as the knob resistor, and a 4.5 volt voltage source. You'll notice pretty quick here that the voltage that we're measuring across both of the LEDs together is smaller than what we predicted. This is because our approximate model, we're actually using it outside of the range that it's most accurate for, which is where this error is coming from. And you'll see that the rest of that voltage is across our 100 ohm knob resistor. Now, one thing that this model is good at showing us is that as I lower the voltage across the circuit at our source down to 3 volts, you'll see that the LEDs get dimmer, and right around 3 volts, we no longer have enough voltage to keep both of our LEDs on. Now, this isn't because there's no current going in the system, like in our model that we showed. There's just not enough current for the LEDs to be emitting light that we can see. So we're going to be going over a more accurate model of the LED in a much later video when it's required, but hopefully this gives you an idea of the difference between our approximate model and what the actual characteristic of our circuit is. If you're watching this in the future when I have the video done on the more accurate model of the LED, you'll see a link for it in the description below and on the video right now. In any case, see you in the next video.